Okay, so let's get into this question. It states that given that we have an array of integers called list, okay, and a target value called, well, target value, and this binary search algorithm, which I'll go into in a bit more detail in a second, it's going to ask which value inside of list, okay, is going to be the third, all right, that's important, the third to be compared to the target value in a binary search for the target value. Okay, so it's a bit of a confusing question, but all it's really asking is when you go through this algorithm right here, there's going to be a certain amount of iterations, and there's going to be values that are compared against other values, and it's asking which is going to be the third one that's compared against this target value. And even if this target value isn't in the array, which again we can see up here, it's not in the array, but that's not necessarily important because it's still going to be compared to a certain amount of values in order for this algorithm to determine that it's not in the array. So I'm going to go over the algorithm in a bit more detail, explain how it works, and then we're going to work through this problem with 60 as the target value, and then I'll use a few more values to kind of help you wrap your mind around it. Okay, so now I'm actually going to go through the algorithm with the example that was provided. So first off, we have our array list, and I've listed the respective index below each value to kind of help you understand. So for example, value 3 has index 0, 5, 1, and so on. Um, okay, and by the way, I've also put a little arrow at the top on each line of code that we're running, so it's easier for you to track. Then our target value is going to be 60 in this case. Next, we're going to start the declaration of some variables. So up here, as you can see, we have mid, low, high, and value. I've colored them slightly differently, and there'll be a reason for that. Um, you'll see why. I'm also not going to explicitly state the purpose of each of these variables just yet, because you're going to be able to gain a kind of intuitive understanding uh, through how I explain it, and I'll clarify it towards the end. Okay, so next, we're going to start our instantiation of these variables. So our low variable is the one instantiated first to 0. Then we have our high variable instantiated to the length of the list minus 1, and we can see that our list is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 elements, and subtract 1, and that's 14. Okay? I also want you to note that I've added little pointers for your convenience. That's kind of why I had the colors. They correspond to the pointers. And also note how the values correspond to certain indexes on the array. Okay, and then so next we are going to go straight into this while loop, and this while loop is going to just check if high is greater than or equal to low. In our case, high is 14, low is 0, which is so it's going to be evaluated to true, and we're going to enter the loop. Next, we're going to instantiate the mid variable. In this case, it's high plus low divided by 2, or sorry, in every case, it's going to be high plus low divided by 2, but in our case, it's 0 plus 14 divided by 2, which is 7. Okay? And then lastly, the last value to be instantiated is going to be our value variable, and that is just going to be the value um, assigned, or the number rather, integer assigned to the value of the list at index mid. So in our case, the index mid is 7, so the value at index mid is 25. So our value is assigned to 25. The next step is to kind of enter a little series of conditionals. So the first condition we enter is we're going to check if our value is less than the target value. 25 is less than 60, which is true. So now we're going to enter this if statement, and we're going to execute this line of code, which tells us that low should now equal the value of mid plus 1. So mid is 7, so mid plus 1 is now going to equal 8, and therefore we've moved that pointer up to 8. And I hope you're starting to kind of see how this works now, because obviously a binary search assumes that the list is sorted, which means if it determines that the middle value is going to be um, less, if the middle value is less than the value we're looking for, then we can just cut out that value and every value to the left of it. Because again, if the array is sorted, these are guaranteed to be less than the value itself, the value we're looking for. Okay, so next we're going to, since we've executed this, we're going to look, okay, else if, else if and else. We don't execute these after an if, we only execute these if the if doesn't execute, right? So now we're going to go back up to the start of the while loop and we're going to check again. So, um, well, high is greater than or equal to low. Well, 14 is greater than or equal to 8, which is true. So now we're going to go through here again and we're going to assign the mid value to, again, high plus low divided by 2, which will end up being 11. Okay, 14 plus 8 divided by 2 is 11. And then again, the value is going to be the list index, or the list at index 11, which is 77. Now we're going to check, is the target value greater than the value, or rather is the value less than the target value? It's not, because 77 is not less than 60. So now we're going to go to the next statement. Um, okay, is value greater than target value? Is 77 greater than 60? Yes, it is. So now what we're going to do is we're going to take our high pointer and we're going to make it mid minus 1. So we're going to shift it to the left. The same concept of why we took the low pointer and took it from 0 and put it to 8 applies here. If the value at our new midpoint, in this case 77, is going to be greater than our target value, in this case 60, then we're going to make high mid minus 1, because again, all of the values that are to the right of that, all the values that are greater, they're going to be too high, because if 77 is too high and the array is sorted, everything to the right is going to be too high because they're all going to be greater than 77. So since high is now mid minus 1, we've narrowed it down to these three values, and we're going to start the loop again. So we restart the loop. Okay, we're going to check if high is greater than or equal to low. 10 is greater than or equal to 8, so we're going to enter the loop. Now the middle value is going to equal high plus low divided by 2. High plus low is 18. Divide that by 2, that is 9. Okay, and then we're going to assign value to, again, the list at index 9. So now we see that everything is kind of getting a bit more concise. This is why binary search is so cool. It kind of like zeroes in on the value, right? So um, now that we've done that, we're going to enter our little control flow, our conditionals here, and we're going to check if value is less than target value. Value here is less than target value because 33 is less than 60, right? So now we're going to do our little operation inside of this if statement, which is saying low is going to be equal to mid minus 1, or mid plus 1, sorry. So low is going to equal 9 plus 1, which is 10. So now our low is here, okay? And we're going to restart that loop again. So 10 is greater than or equal to 10, which means we enter the loop again. Mid is high plus low divided by 2, which means mid is going to be also 10, and value is list at mid, which is going to be 55. And now we're going to check right here. Okay, 60 is greater than 55, so our low is going to be mid plus 1. And then we're going to restart the loop again. And now we enter uh, here where we see that 10 is not greater than or equal to 11. So we're no longer in the while loop, and we haven't returned anything within the while loop, which means we're just going to jump all the way down here to return -1 because the value was never found inside of this loop. So now I kind of want to circle back to our original question because I kind of explained the whole binary search thing, but we still don't have the answer to our question. So I'm just going to answer that real quick. So we can skip through all this. We know the list, we know the target value, right? We know what these do. Okay, so we have all of our values and we're just going to find where things are compared. So if you haven't noticed already, when the things, or rather the values are compared to the target value, uh, only here and here, which means these are really the only things we need to pay attention to, right? So we're going to basically go through the binary search as I explained to you earlier, but now all we need to do is just keep track of the values that are compared. We'll enter the while loop, we'll have our values, and here is the first check. So 60 is going to be compared to 25. So uh, we can say the first value it's compared to is 25. I'll just write it on the top right up here. Okay, so first value we compare 62 is 25. Now we restart our loop again, right? Um, sorry, restart our loop again, and then we're gonna go here again. Okay, 60 is now compared to 77, so that's the second value it's compared to, right? So um, we have 25 and 77. Now, sorry that it kind of goes off screen every time. I apologize for that. Um, but yeah, we'll just remember this for now, 25 and 77. So now what we're gonna do is go here, okay? So we have from before 25, we have 77, and then the third value that we are comparing target value to is 33, okay? So 25, 77, and 33. And since 33 is the third value we're comparing to the target value, you would end up entering 33 into the answer box. Okay, so I'm just going to give a quick little example of if the target value actually is inside of this array. Okay, so just one thing, I'm not going to include all of the extra value tracking and everything like that because it's fairly easy to track everything with an array of this size. So I'm just going to basically show you how you would go about it, right? Okay, so our target value is 7. To start off, our left, our low pointer is always going to be at 0, and our right one is always going to be at whatever the length of the array is -1, so the last index, and then the mid is going to be 0 plus the length of the array -1 divided by 2, which 0 plus 14 divided by 2 is 7, okay? So our midpoint is 7. So what we're first going to do is we're going to check if our value is less than target value. So 25 is not less than target value because 25 is not less than 7, which we remember, if the value is greater than our target value, then we can basically cut off everything here, which means taking our high pointer and moving it to mid -1. Okay, then we're going to get our new mid, which is going to be 0 plus 6 divided by 2, which in this case is going to end up being 3. Okay, I'm going to delete the value pointer because it's basically just the same as the mid pointer in this case. It's not exactly the same, obviously, but for all sakes and purposes, in our case, it should be fine. So now we have 0, 6, and then we have our midpoint at 3. So again, let's compare if this is less than 7. Again, no, it is not less than 7, right? So since it's not less than 7, we can take this, okay, um, and then we can drag this here, right? And then um, mid is going to be 0 plus 2 divided by 1, okay? And just a quick little note, the way we're keeping track of if high is greater than or equal to low is literally just if low is to the left of high, right? If this were here, then we know the loop wouldn't be executing anymore, and we would return -1 because we wouldn't have returned um, the value's index if it was found, right? So, okay, now we're going to check, is 5 less than 7? 5 is less than 7, which means we can move our low pointer now to mid +1, which is here. And then mid is going to be low plus high divided by 2, which is 2 plus 2 divided by 2 is just 2. So now mid is here. Okay, now it's going to check, okay, is 7 less than 7? No. Is 7 greater than 7? No. So the last thing we can check is if 7 is equal to 7. And if 7 is equal to 7, then we return mid, which is going to be the index of the value, because that's ultimately what the goal of binary search is we're finding the location of the value within the list, right? So we find this 7 does equal 7, so we return 2. Now you might be wondering why, right? Because we have this big like advanced search algorithm, right? And when we've learned to just kind of do something like this, public static, the declaration of the method looks fairly similar. And then we just kind of do, we do for I equals 0, I is less than list length, I plus plus, right? And then if if list at index I equals target value, then we can return I, right? And then down here, we just return -1 for if the value is not in the array. And now, if I were to run this, right? So let's run our binary search algorithm. Let's run it with a value that's in there, right? 77, okay? Um, and if I run this, we see, okay, 77 is at index 11. That's right. Now, if I do same thing with our linear search, and we do the same thing, list 77, and we run it, it's going to print out the same thing, right? So you're probably wondering, okay, why do we have these two things to do the same thing? Now, I want to kind of propose an idea to you, okay? So suppose we have this list, and ignore that target value, actually, pretend it's not there. So let me just like erase that, right? Okay, so let's say our target value is actually, like, let's say it's 89, which is all the way at the end of the array. So 80, oops, I can't even draw. 89, okay? Excuse my bad writing. So to actually find 89, right, we have we have to kind of, with a for loop, we have to go from 3, okay, 3, not 89, 5, 5, not 89, 7, and we have to do that all the way for every single value until we reach 89. Now, I want you to imagine, think of this list, pretend it's like a million values. You're having to go through a million values at the worst case to get to the last value. Now, obviously, you could get lucky, right? The value you're looking for could be the first value, and you just have to look for one, and then bam, you have it. Okay. Um, but on average, you're going to be looking through this quite a bit. So basically, pretend um, we have a length of any given array, and let's call that n. And every time we have to check a value, so we're checking if with a for loop, we're checking if each value is equal to our target value, then that's called an operation. So I'm going to introduce this notation to you called big O notation. And that's what this right here is, okay? So we have this, we have O of n. So we call a linear search, which a linear search is just going through every element and checking if it's equal to our target value. O of n is the time complexity of a linear search. And the time complexity just means how much time it takes. And a good way to imagine this is um, pretend you have a certain amount of values, and say, again, in this case, you have 15 values, right? You have 15 values to go through, and pretend we're using like some super old computer on some super old hardware, and uh, it just takes 1 second to go through each value, one full second, right? So 15 times 1 second is going to take 15 seconds. Now you're like, okay, that time's trivial, but again, think of if we have an array with something like a million elements, right? We don't want to have this O of n time. We don't want to have to do a 1 second operation for n amount of elements. We want to just be able to find it fairly fast, which is why we introduce binary search. And you may think, oh, but it has a lot more code, so it can't be faster. Well, more code does not necessarily mean slower. So, um, what I am going to propose we do is show how binary search works and why it's so much faster. Okay, so for a binary search, as we saw before, it kind of cuts everything in half, right? So we're going to check 89 compared to 25. Obviously, it's greater than 25, so we can just kind of cut off everything over here. And now we're just focused on this. Now we have the midpoint, which is going to be 11. 89 compared to 77, it's still greater. So we just cut off everything on this side. Now we're just dealing with these three. Uh, we're comparing it to this midpoint. Again, it's still greater. So now we're just comparing it to 89 itself. And 89 does equal 89. Um, so it's at the end of the array, but we only ended up performing a few operations. We performed one to compare it to the initial value. We performed one more to compare it to the middle value of the right side, one more to compare it to the middle value of the right side of that right side, and one more to compare it to itself at the end. So comparing that to 15 operations, right? Um, which again is O, sorry, 15 operations for an array of size 15. So that's what we call O of n, which is again as many operations as are elements in the array. So we're going to compare that to something we only did a few elements for, which in this case was, yeah, which in this case was 4 operations, right? Now, okay, 4 seconds versus, again, say 15 seconds. We're just pretending it'll take a second to do each operation. That's a good difference, but it's not a big amount of a difference. So where it really shines is with really, really, really large things, okay? So just for an example, show you the contrast. Again, if we have an array of 1,000 elements and it takes 1 second to perform each operation, that's going to take 1,000 seconds, okay? And with our thing before, we only had to perform 4 operations with 15 elements, right? So now we're going to try to find the complexity of binary search. If you've noticed, binary search, again, it's splitting it in half every time until it gets to one element, right? So we have an array of 15 elements, so we can do 15 divided by 2. So now we have 7.5. So 15 divided by 2 is 7.5. Um, now 7.5 divided by 2 is 3.75. And now we're going to do 3.75 divided by 2, which is 1.875. And then we divide that by 2, which is approximately, or not approximately, which is um, 0.9 uh, 375. Now, this we can notice that's a very close number to 1, right? So we're basically saying, okay, we divide the array into 2. So now we have approximately 7.5 elements to deal with. Now 3, now 1.875, now 1, right? So again, we're just um, doing one operation, so dividing by 2, dividing by 2, dividing by 2, dividing by 2. Uh, that's basically how it works, right? Because once we get to here, we know it's equal. We don't have to do anything. So if you like math, you might be able to see where I'm going with this. So if we see that's being divided by 2, which means, and we're multiplying 2 by a certain amount of times, right? So 2 times 2 times 2 times 2, that's just 2 to the 4th power, right? So now, since we have that, we see that dividing by 2 4 times is 0.9375. So we can assume that obviously 0.9375, that's not the exact value, so there might be some decimal missing, but we can assume that 0.9 0.9375, okay, um, times 2 raised to the fourth power is approximately going to be equal to 15. To be exact, it's without having, all of the decimal values of 0.9375, it's equal to 14.984, but you get the idea of what I'm saying. So, um, with the concept of logarithms, um, we are basically saying we have a logarithm of a base of a certain number. It's basically saying this number to the power of what, which is going to be this number, is going to equal this number. So we can kind of take that logic. So since we see it's being divided by 2 every time, we can say log base 2. Right here, we're just wanting to get to the amount of numbers, right? So we have 15. So an array of size 15 equals what? So log base 2 of 15, guess what that number is? Well, that number is 3, or approximately 3.906, and then there's a bunch more numbers. Notice that even with all the imprecision of the kind of math I'm doing here, we have this, and that is nearly the exact amount of operations we needed to do to get to our number. So, or to this number, sorry. So, because that's how many times we're dividing to get to a number, that's basically 1. So, with all this said, we can basically conclude that the amount of operations you have to perform for a binary search is logarithm with a base of 2 of however many elements or numbers or whatever you're using. And remember how we represented the linear search as an O of n? We just represent this as an O of log n. And if you're wondering why I'm not putting the base of 2, it's just because in computer science, generally 2 is used as the default base as opposed to math where it's like 10. Just a little discrepancy there. So a binary search is O of log n. Now, why is that so impressive? If you need to kind of visualize that, um, let's say we have 2,000 values, okay? Log base 2 of 2,000, I believe, is something like uh, 10, or no, I think it's 11, if I'm remembering correctly. Um, yeah, log base 2 of 2,000 is going to be about is going to be about 10.965 and so on, right? So now, um, since we remembered we were dividing by 2 every time we obviously we divide by 2 every time we perform an operation, we can kind of take that same logic when it comes to the things we're applying, which means every time we double our n, our value, we only are adding a single operation, right? So just a few examples. I won't go through them all manually, but so we double 2,000, we get to about 12 operations. Double that, we get to about 13, and we can go all the way up, even until we get to a million operations, and it will only, or rather, sorry, a million values or elements, and it will only take about 20 operations, which, to put that in perspective, again, a linear search with the for loop, that would take 1 million operations. So that's pretty incredible compared to a linear search, and I think it's one reason why a binary search or even other searches are going to be so efficient, and I hope that this kind of found this a bit interesting of why we want to optimize our programs.